right, so as a continuation on our discussion of searching and sorting, today we are talking about some different sorting algorithms. So, like I said, last class we talked about our two big categories, searching and sorting. Last class we talked about searching using the linear search algorithm. Today we are going to be talking about a couple of different sorting algorithms, where sorting involves putting all of the elements in some kind of a collection, whether it's an array or array list, putting them in order, whether it's going to be numerical order, increasing, decreasing, whether it's alphabetical order, we're working with strings, or some other kind of comparison that we're making. And today we are going to be covering two different sorting algorithms that we can work with. Now, don't skip that slide. As our data sets grow bigger and bigger, it is increasingly difficult to find whatever values we're looking for. Algorithms like linear search are most useful when our array is not sorted, and linear search is not very efficient. If we put our elements in order, if we sort them, we can implement a much more efficient searching algorithm, making our data much easier to find whatever we're looking for within. So sorting is very helpful because it enables us to search way more efficiently. So today we're talking about two different sorting algorithms. We're talking about selection sort, and we're talking about insertion sort. And we're going to go through how they work and how we can implement them today. So selection sort works by finding the smallest element in a list, and then we move it to the front. And we're going to repeat this over and over again, finding the next smallest element and swapping it up until the front, over and over until we have reached the end of the array. So let's say I have the list or the array 8, 2, 4, 6, 1, 3. First thing we're going to do, we're going to start with our current index at 0. So this is the place we're going to swap something into. So we're going to look through our array, we're going to search and find the smallest element. The smallest element is that 1. So we find the current index, we find the smallest index, and then we're going to do a bit of a switcheroo. We're going to take whatever value was in that position, slot it in here, and vice versa. So now that index 0, is sorted. So everything that is in blue is now sorted, so we can move on to filling in the correct value in this position. So our current index is 1, and our smallest value is in that exact same spot. So we perform a switcheroo. We really don't need to do a switcheroo because we already have the right thing in the right spot. But hey, we now have that thing in the right position. Now everything in blue is once again sorted. And we're going to repeat this over and over again. This is our current index. Our smallest value is 3. So we swap those. Now that's sorted. Current index, our smallest value is 4. Now that's sorted. And we swap those. And hey, wouldn't you know, since there's only one element that's left that isn't sorted, it must belong at the end of the array. We've swapped back and forth over and over, and this is the only quote-unquote unsorted element. So it has to go at the end anyway. So we can stop our algorithm here because we know everything up until this point is sorted, and if there's only one thing left, of course it's going to be sorted as well. So that's a visual kind of walkthrough of how selection sort works. So let's actually implement it. Let's show how it might work with real code. So here's our pseudocode. Here's our description of how it works. We are going to traverse through each index until the second to last element. Each time in the loop, we're going to find the minimum in the remainder of the list, and then we are going to swap the value at the current index and the value at the minimum index. So let's fill in each of these pieces one by one. Traversing through each index, that's pretty simple. We're going to do a for loop for this. For I equals 0, I less than array length minus 1. We don't need to go all the way to the end. And then we say I plus plus. Finding the minimum in the remainder of the list. So this is going to be a several part step. So if we're finding the minimum value in the rest of the list, first we're going to assume that the one we're looking at, the current index, is the minimum. So we make a minimum variable and we assign it the value of I. So we're assuming current index is the smallest. Then we want to loop across all of the other values, all the other indices in our array. So we're going to do another for loop for int j. That should start at I, not at 0. J less than our array length, and then we increase j as you either start at I or even I plus 1. We don't really need to compare the value of I against itself. Then we can check if the array at our current j index is less than the array at our minimum variable. If array at j is less than array at min, then we will reassign min to equal j. If we ever find a smaller value, we're going to remember it. This is just the finding the minimum algorithm that we've talked about in the past. So we're going to take this, we're going to slot it in here. Then we are going to, after we've found the minimum index, we have our current, we have the place we want to swap with, I and min, then we need to actually do that swap. In order to perform a swap in Java, we've done this before, we need to make a temporary variable to store the value of 1. We're going to copy the value from the minimum index into the current spot and the temporary into the minimum spot. So we make a temporary equaling whatever's at index I. We say our array at index I is going to equal whatever was at the array at index of the minimum value. And then we copy that temp value into our array at the minimum index. And the reason we can't just say array at index I equals array at index min, and then array at min equals array at I, is because we already did this assignment. So if we don't save the value that was at I into a separate variable, we will lose it. So we save it in a separate variable, then we overwrite it, and then we use the value we saved to overwrite the other position. So there we have it. There is our selection sort algorithm. We are looping over all our elements up until the second to last one, finding the smallest value after the current one, or the smallest element in our array list, or smallest element in our array, going up after the current place, and we are then swapping. We could even turn finding the minimum and performing that swap into methods of their own. We could take those chunks of code, make them into their very own method, find min and swap, and there we have. That would be that would let us save some space in our algorithms programming code here. So if we kind of visualize how selection sort works, we can see it's performing these swaps over and over again until everything is in order. You can see the values getting swapped into their correct spots in the beginning, and things are getting generally swapped when they're bigger towards the end, until we eventually reach a completely sorted sequence here. So does selection sort make sense? This is one of the simpler sorting algorithms. All right. Now, insertion sort is going to work by assuming that everything to the left of the current index is already sorted. And then we're going to insert values into their appropriate positions when we see them. So let's do a visualization of this one as well. We've got that same starting list, 8, 2, 4, 6, 1, 3. So we're going to start our current index at 1, because if we just look at the array, a one element array, just element 0, this element, that array, is definitely sorted within itself. If there's only one element, it's of course going to be sorted. So anything to the left of our current value is, we're assuming, it's already sorted. So in our code, we're going to essentially slide this down the array until it reaches its proper position. So currently, we're going to shift this into the right spot. This should be moved to the left. And now everything at and before our current index of 1 is sorted. Then our current index can increase. We're going to shift this to the left. And hey, that's its correct spot. We don't need to move it any further left, because otherwise 4 is bigger than 2. We don't need to go any further. That area is now sorted. Our current index increases. We're going to shift that left. Now that is in the correct place. We don't need to shift it any further. Current index increases to 4. Then we shift 1 left. We can keep shifting left until it reaches its appropriate location, because we don't want it to stop until it has reached that smallest spot, because it is smaller than anything else that we have seen in the array. So now, once it has fully shifted into the correct position, now everything 4 and below is sorted. And then at index 5, we start it shifting, shifting, shifting until we see a value that is smaller than what we're looking for, or than our current value. At which point we stop and say, hey, we have made it. Our whole array is now sorted. Does this process for insertion sort make sense? Yes? No? Please let me know if you want me to go over that again. I would be happy to explain it again. Or we can just look at implementation. I'm going to take your resounding silence as, hey, let's look at implementation. So, when we're implementing through our insertion sort, we're going to traverse through each index starting at 1. So we're going to start at index 1 and go up until the end. And then inside of there, we're going to look backwards through our sorted elements to find where the current element should be placed. And we're going to shift our elements in order to place the current element at the right position. So traversing through each index starting at 1, that's pretty simple. We want to start I at 1, loop while I is less than our array's length, increase I by 1 each time. Then we want to traverse through the sorted elements to find where our current element belongs. So we're going to start and say our current value is the array at the current index. So let's say I have 1, 3, 9, 8, 7, for example. So let's say we have already sorted those two into place. We're looking here. Current val is going to equal 9, and our sort index is going to equal I minus 1. We're going to assume that I minus 1 is our place we want to place our value. And as long as our sort index, the place where we are going to sort it into, is greater than -1, and array at the sort index is greater than our current value. So as long as we haven't reached the very beginning, and as long as the things we're looking at are bigger than our current value, because we want to keep going until we find something smaller, because that's the place we know we're going to insert it. Then we're going to say our array at index sort index plus 1 equals our array at sort index. So let's unpack that. Our array at, if this is our current sort index, I'll use a different color for that. If this is our current sort index, our array at sort index plus 1 is going to be here. That's going to equal array at sort index. Now, I realize this is not a great example because this condition is already false. So we skip the while loop there, essentially. And we say array at sort index plus 1 equals current val. Right now, we're just reassigning that to equal 9. Let's do the next one, because that's actually going to accomplish something. So our I will then shift to here. Our sort index is going to be here again. Now, our sort index is greater than -1. That's true. And our array at the sort index is greater than our current value. Current value is going to equal 8 right now. So we're going to say array at sort index plus 1. That's here. Equals array at sort index. We're going to copy that 9 over here. And sort index goes down. So then we check, are we still in bounds? We're still in bounds. And is this value bigger than our current value of 8? 3 is not greater than 8. So our condition here is false. We exit the loop and we say at index plus 1 or sort index plus 1 is going to equal our current value. So we've shifted 8 in here. So we're not shifting it individually all the way down. We're shifting everything up until we have found the correct place to place it, and then we insert it into that spot. Does this implementation make sense? Any questions on how this works? Cool. Okay. Now, if we visualize insertion sort, we can see our sorted kind of area on the left is growing larger and larger, encompassing all of the new values that we are going over until we've reached the very end, at which point everything has been put into our array in its correct position. Everything is now sorted. All right, if we do a little bit of a comparison between the two, those did not start at the same time. Can I make them start at the same time? No. Well, here we have two visualizations of our two different sort types, and if they don't start at the same time, it's really hard to compare them. Now, insertion sort and selection sort each have a use case in which they are more useful. Their individual efficiency is going to be based on how sorted the list is at the beginning. So if I have two arrays, the other one's kind of hidden right now, but if the array is almost sorted to begin with, 0, 1, 2, 4, 3, then insertion sort is going to end up being more efficient here. Because with selection sort, we would have to look through everything and check, is anything smaller than this thing? And then we go here, is anything smaller? And then here is anything smaller, and so on. Where with insertion sort, we're going to start here and check, is this in the right spot? Let's loop until we find the right spot. Oh, wait, we don't need to run that loop. And then for this one, oh, we don't need to run that loop. And then for this one, we don't need to run that loop. And then here, we only need to run the loop one time to swap the 3 and the 4 into their correct position, or to slide the 3 into its correct spot. So overall, our number of statements is going to be way, way lower. With another array, if I have my array in reverse order, 4, 3, 2, 1, 0, selection sort is going to execute fewer overall statements, because we're going to go from here to 0, 3, 2, 1, 4, 0, 1, 2, 3, 4, and then our array is sorted, but it's still going to go through the rest. So we started here, 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 0, 1, 2, 3, 4, and 0, 1. Actually, we don't need to do it again. That is the last one. Now, that works pretty well, but insertion sort is going to shift every single element all the way down the array. So 3 is going to need to get shifted into its position. Then 2 is going to need to get shifted all the way down, and then 1 is going to need to get shifted all the way down, and then 0 is going to need to get shifted all the way down. So we're going to have lots of execution statements, or statement executions, that happen when we do insertion sort on a completely backwards list. So that's the worst case scenario for insertion sort. So when we are determining how efficient an algorithm is, a tool that we can use is saying how many statements are going to execute in the worst case scenario for this algorithm. This is a useful tool for us as programmers for just kind of analyzing how efficient an algorithm is likely to be. Usually, we're going to frame this count in terms of how long the array is. So as the size of my as the size of my array increases, how does the statement count of my algorithm increase? Is it linear with the size of the array? Is it multiplicative? Do I have is it doing an exponential growth? So we're not going to get hugely in detail at the moment, but just being aware of counting the number of statements that execute is a pretty good way to determine how efficient an algorithm is based on the worst case scenario. All right. Any questions on that either? All right, then I will stop our recording.